Previously in this course we discussed secret key cryptography. Secret key cryptography is fairly easy to design, but it has a huge disadvantage. It requires prior exchange of secret keys between the two parties. And clearly, this is not appropriate for internet communications. So we secure our internet communications with public key cryptography that does not require prior exchange of keys between the two parties. The idea of public key cryptography is that we generate two keys. A public key, which is required for encryption, and a secret key, so which is required for decryption. So a public key is public, so that is, it could be posted on a website or embedded into website code. Whereas a complementary secret key is kept secret. Now imagine the following scheme. Alice wants to run an internet store and wishes to receive credit card numbers from her customers. So to do it in a secure way, Alice generates a pair of this public and secret keys. So she publishes her public key on the store's web page. So basically, whenever you see an URL address that goes HTTPS, so this means that this website has an embedded public key in its code, right? So then, and obviously, so she keeps her secret key secret. Bob, Alice's customer, encrypts his credit card number using the published public key, and sends the encrypted message to Alice. So Alice uses her secret key to decrypt Bob's credit card number. So clearly, there should be some sort of a match between the public key and the secret key, so that together they allow encryption and decryption of the same messages. And the trick here is to organize this scheme in such a way that a secret key cannot be easily recovered from a public key. Basically, here everyone is able to encrypt any number of messages using the same cryptosystem. So with secret key cryptosystem, usually if you are able to encrypt messages, then you can infer information how to decrypt the messages as well. In a public key cryptography, so this is the point, that even if you can encrypt messages, you still do not have enough information to obtain the secret key. In public key cryptography, the secret key is theoretically determined by the public key, but computationally, finding the secret key from public key is infeasible. So the algorithm that will do that is too slow to be run in realistic time. Now let us discuss in detail RSA Cryptosystem. So this is a public key cryptosystem that is widely used to secure internet communications. We begin building RSA Cryptosystem by generating two large prime numbers. P and Q. Now, generating prime numbers is fairly easy with a good computer. So it turns out that there are many prime numbers out there, and we have fast tests, fast probabilistic tests for primality testing. So this means that we can take numbers that we suspect to be prime, and we can test them to be prime with a very high degree of certainty. So this takes no time at all. And so then we set n to be the product of these two primes. If we are given n, but not its factors, then we can fairly easily see that n is a composite number. It will fail the primality test. But we have no good algorithm for finding the factors p and q if n is a product of two large primes. If we had a computational ability to factor n, then RSA cryptosystem will be broken. In internet communications, any message is a long sequence of zeros and ones. In order to use RSA cryptosystem, we want to convert this binary stream into a sequence of remainders mod n. So let us see how we can do this. So suppose this n is between 2 to the power n and 2 to the n little n plus 1. So then we split our binary stream into blocks of n bits in each block. So then each block may be treated as an integer in a binary form. So each integer in the sequence is less than 2 to the power n, right? So because an n-bit integer does not exceed 2 to the power n, which is less than n. And so may be viewed as a remainder mod n. Right. So now, this integer defines a remainder. In RSA Cryptosystem, we will be encrypting each block in the same way. So now we come to the task is that now we need to encrypt a remainder m mod n. Right. So now each block is viewed as a remainder mod m. So we'll be encrypting each block in the same way. So let's just focus on a single block, which is a single remainder. So now we want to build a cryptosystem that deals with remainders mod n. Let us look at the multiplicative group of remainders mod n. Right. So the order of this group is equal to p minus 1 times q minus 1, which is equal to n minus p minus q plus 1. Now let's call this integer capital M. Then by Lagrange's theorem, so we know that for every a in Zn multiplicative, a to the power m is equal to 1 mod n. Now, for the public key, so we generate a large random, well, possibly prime k in the interval that k is between 1 and m. So basically, k is less than m, but comparable to m in size. And we possibly could choose k to be a prime number. To generate the secret key, solve the following equation. So k times s is equal to 1 mod m. Right. So basically, s, the secret key, is k inverse mod m. So what we need is that this k is invertible mod m. And for example, if k is a prime number, then certainly it's relatively prime to m and will be invertible. So this s is easy to compute using Euclidean algorithm if we know the value of m. Now we have a pair. So we have a public key k and a secret key s. Well, strictly speaking, n is also considered to be a public key. What is our encryption process? So here we want to encrypt a remainder m mod n. So to encrypt m, so this is a block of our message, compute m to the power k mod n. So this will be our cipher block C, and it's also a remainder mod n. Now we see that in order to perform this encryption, we only need to know the values of k and n. So here is our decryption method. So to decrypt C, compute C to the power S mod n. Now we claim that this will give us back our original message m. Let us see why this is true. All right, so let us look at C to the power S. Well, C is m to the power k. So we have m to the power k to the power s. So this is m to the power ks. But k and s were chosen in such a way that k times s is 1 mod m. So this means that ks can be written as 1 plus d times m. And so then these factors is m to the power 1 times m to the power capital M, all raised to the power d. But here we have Lagrange's theorem. So Lagrange's theorem says that for every element in this multiplicative group, a to the capital M is equal to 1. So what we get is m times 1, right? And all these computations are done mod n. So we get that this is equal to m mod n. And so we see that our decryption process returns the plain text block m that Bob was sending. So this is part of unencrypted message. So let us analyze the security of this cryptosystem. So we claim that the security of this cryptosystem is based on our ability or inability to factor n in a product of two primes. So if we are given the product, find the factors. So there are no published algorithms that tell how to do it in reasonable time. Of course, here we mean no classical algorithms, because this is exactly what Shor did with his quantum algorithm. Shor's quantum algorithm does allow us to find the factors of a large integer in polynomial time. But for now, let us assume that this factorization problem is computationally intractable. So the question is, can we extract the secret key if we know the public key k? Well, here, so this says that S is just k inverse mod m. So if we know m, so this number, then certainly we can compute S from k. So this is exactly how Alice will do this. So now we come to the question of, so can we determine the number m? It turns out that if we can determine the number m, then we can do the factoring, and vice versa. So if we can do the factoring, that we can determine the number m. So finding this number m is actually equivalent to factoring. So let us see why. So, well, n is publicly known. So if we know n and m, then we can figure out what's p plus q, right? So p plus q is equal to n minus m plus 1. So, but now, if we have n and so p plus q, let's call this L, right? So then we can consider the following quadratic equation. So let's take x squared minus L times x plus n is equal to 0, right? So this, so L and n here are integers. So we consider this quadratic equation. So it turns out that this quadratic equation has factorization x minus p times x minus q. And certainly we have a simple computational formula for computing the roots of the quadratic equation. So if we can form this quadratic equation, then we can find its roots, and its roots are going to be p and q. So this means that if we know both m and n, then we can form this quadratic equation with n and L as coefficients, and by solving this quadratic equation, we obtain the factors p and q of n, and then the cryptosystem is broken. So this tells us that we can find a secret key S from a public key k only if we can factor the integer n in its prime factors. Let us discuss another potential pitfall of this method. So here we said that our block m is an n-bit integer. But in our computation, so when we show that we can decrypt m after encryption, so we assume that m belongs to Zn multiplicative. So this means that m is not divisible by p or q. Certainly, we are not going to allow m to be 0. Well, this can be achieved by, say, adding 1 to each block. Since p and q are very large primes, so the probability that a random integer m is divisible by p or q is extremely low. And indeed, our method may fail with a very low probability, right? So if m is divisible by p, then our method will fail. But here we observe that if we can achieve such a failure, right? So if we can achieve this accidental failure, if we can generate in a random block that's divisible by p, then we can determine p, because p will be GCD of n and m, right? So if m is divisible by p, then the greatest common divisor of n and m will be p. And computing greatest common divisors, again, is easy using Euclidean algorithm. So this tells us that if we can achieve the failure of RSA Cryptosystem, then again we will be able to factor n, because if we can find one factor, then by just dividing we can recover the second factor in an easy way. So this tells us that we may very well assume that accidental failures do not happen. Now, this is the RSA Cryptosystem. So here we recall that we encrypt blocks by raising them to the power which is our public key, and we decrypt messages in a very similar way, only we raise cipher blocks to the power of a secret key. And all computations are done with remainders mod n. Classically, we do not know an efficient algorithm for factoring large integers. So let us discuss some preliminary ideas of Shor's algorithm. So what is our goal? Our goal is to find m, right? So which is the order of this multiplicative group. So the idea for finding this order is again based on Lagrange's theorem. That says that order of every element A in the group G is a divisor of the order of G. And suppose we are able to determine orders of elements in this group. And so then we take several elements, say A1 up to AR, and we find their orders. And then we take least common multiple of these orders. So then this will be a divisor of the order of G again. But usually this will be not far off from the order of G. So statistically, we're going to capture here all large prime factors of the order of G. And so the difference between these two numbers will be just a product of some small primes. So then, if we compute this number for a reasonably large R, then we can easily determine the order of G by simply guessing. So the point is that the value of M is not known to us, but the magnitude of this value is known, because what we see here is that M is approximately equal to N. So now we come to the task. So given element A in our group, well, in this case the group is Zn multiplicative, find the order of this element. If we can perform this task, then we can find the order of the group. So if we want to solve this problem classically, then we compute a sequence A squared, A cubed, and so we have to go all the way up to A to some power R, which is equal to 1, right? So this is what we want to achieve. And realistically, this is not going to happen. We don't have sufficient time to complete this task, because this R could be comparable to these numbers, M and M. And so this means that in theory, this is how to do it, but in practice, this program will never complete. When we do it on a quantum computer, so the idea is that quantum computers have huge memory, and they can run massively parallel computations. So this means that on a quantum computer, we can compute all of this and more. So we compute and store simultaneously this sequence. So A squared, A cubed, A to the power R, which is 1. And then A to the R plus 1 will be again A squared, again A to the R, which is 1. And then again A squared, And what we do is we compute many iterations of this. And this is done not sequentially, but in parallel, in just one iteration of an algorithm. And then what we get is we get a periodic sequence. But this periodic sequence is hidden, right? So we know that there is a 1 somewhere, but we simply cannot access this, this location, right? So in quantum memory, we have a problem with access. So now we know that we have a periodic sequence, but we cannot locate positions where we have 1. So instead, the idea of Shor was that perform Fourier transform. And the point here is that Fourier transform of a periodic sequence is something that's very nice. And so then, using this Fourier transform, so we will be actually able to find the value of R, so which is the period of this sequence and the order of this element. So we will discuss the details of the Shor's algorithm and Fourier transforms and quantum Fourier transform in future lectures.